On a Calc 3 final exam, I can 95% guarantee you that you'll be asked a question of this nature. Consider the triple integral, some region t, z squared dv, where t is the region described in Cartesian coordinates by x greater than or equal to 0, y greater than or equal to 0, z greater than or equal to 3, and the sphere bounded by x squared plus y squared plus z squared is 12. Now, we need to write this triple integral in Cartesian, cylindrical, and spherical coordinates. So, most certainly you'll be asked a question on the exam where you're given some region and you need to write the triple integral in Cartesian, cylindrical, and spherical coordinates. So in this video, I'm going to show you how to solve questions of this nature, and I have two examples regarding this. So this is the first example. So first of all, let's do Cartesian. Some people like to call it rectangular coordinates as well. It doesn't matter. I'm going to give you a rough sketch of what this region T looks like. So let's say this is Z. This could be 0. It really doesn't matter, actually. And this, let's say this is the sphere. And let's say Z equals 3 is somewhere here. And this is x squared plus y squared plus z squared is equal to 12. This is the region we're asked to integrate. Okay, you know what? I'm actually going to draw this diagram on here because just so it doesn't affect with what I'm trying to do. So z and z equals 3 is somewhere here. This is what we're asked to do. So Cartesian coordinates, we can do it in any order we want. So for convenience sake, I'm going to do it in the order of dz, dy, dx. Z squared dz, dy, dx. In double and triple integrals, the integrand is never affected. So looking at this region T right here, on the z region, it's bounded above by this sphere x squared plus y squared equals 12. So bounded above by 12, root 12 minus x squared minus y squared, and bounded below by z equals 3. On the xy plane, we have something that roughly looks like this. I'm going to label xy plane. X, y. So the projection of this region T on the xy plane, well, when z equals 3, you have x squared plus y squared plus 3 squared, or 9, is equal to 12, and x squared plus y squared is equal to 3. So this is basically a circle of radius root 3. Looks something roughly like this. So root 3, you know what, I'm going to draw this 3 better, and 0. And on the xy plane, looks roughly something like this. So on the dy, so bounded below by y equals 0, and above by root 3 minus x squared, and x is from 0 to root 3. So this is what it is in Cartesian coordinates. Now let's go to cylindrical coordinates. In cylindrical coordinates, what we have is basically this kind of manipulation. So x would be r cos theta, y equals r sine theta, and z still remains the same. Cylindrical coordinates is basically like polar coordinates in 2D, but you add a variable z at the end. And now dv is equal to r dz dr d theta. In polar coordinates, it's r d theta. Here in dv, you just add a dz. That's the only difference. So here, let's I have what I wrote in the rectangular coordinates. Z squared dz dy dx. So x squared plus y squared is r squared in cylindrical coordinates, so 12 minus r squared, and still 3, z squared r dz dr d theta. Okay, so now r, so for the xy plane, look at what I drew here when I was doing the Cartesian coordinates. You have a circle, like the radius goes from 0 to root 3. And here, theta goes from 0 to pi over 2. So this is cylindrical coordinates. Now lastly, we have spherical coordinates. So spherical coordinates, I'm going to write down what happens in spherical coordinates first. So x is equal to rho sine phi cos theta. Y is equal to rho sine phi sine theta. And z is equal to rho cos phi. You know what, I'm going to say x squared plus y squared plus z squared equals rho squared. And dv is equal to rho squared sine phi d rho d phi d theta. This is something you have to remember for spherical coordinates. So in this region E, what we have here is when we have x squared plus y squared plus z squared is equal to 12, this gives us rho squared is equal to 12, which means rho is equal to root 12, or you can say 2 root 3. This is what this sphere looks like in spherical coordinates. On z equals 3, this plane z equals 3, we have rho cos phi is equal to 3. So that means rho is equal to 3 secant phi. So what we have here in spherical coordinates is equal to z is equal to rho cos phi, so this is rho squared cos squared phi times rho squared sine phi d rho d phi d theta. And let's figure out the bounds. So theta in spherical coordinates works exactly like theta in cylindrical coordinates. So theta, I know, goes from 0 to pi over 2. So rho measures the distance from the origin. So it's the lowest bound would be at z equals 3. In spherical coordinates, that translates to rho equals 3 secant phi. And the top is root 12 or 2 root 3. So now, lastly, we need to figure out phi. So phi is the angle from the positive z-axis. So the minimum angle is basically 0. And let's look at, lastly, what this top angle is. So for that, we need to look at the intersection between x squared, the sphere x squared plus y squared plus z squared is equal to 12, and z equals 3. So in that case, we'd have x squared plus y squared is equal to 3. Which means that when you do this in spherical coordinates, we have rho squared sine squared phi is equal to 3. We found out that rho is 2 root 3. So 2 root 3, I'm running out of space, so that's why I'm like, dude. So that's 12 sine squared phi is equal to 3. And when you do this, you get that phi has to be a non-negative value. It's equal to pi over 6. So it goes from 0 to pi over 6. And this is our answer in spherical coordinates. Alright, so I have a second example here. This time I've attached what the region looks like on the side. So let's consider the triple integral E x dv, where E is inside the cylinder, x squared plus y squared equals 4, bounded above by the plane z equals x and below by z equals 0. Let's write this integral in rectangular or Cartesian, cylindrical, and spherical coordinates. So let's start off with the Cartesian. Once again, dz, dy, dx is the easiest order to integrate, so that's what I'm going to do. Let me just write this down. X dz, dy, dx. So the z, I'm going to go from 0 to x, bounded below by the plane z equals 0, and above by z equals x, so 0 to x. dy, so let me just draw the xy plane again. This is what it looks like. Looks something roughly like this. So this is basically from, y, it's negative 4 minus x squared to root 4 minus x squared, and for x it's 0 to 2. This is what we have for Cartesian coordinates. Let's do cylindrical coordinates now. Cylindrical coordinates, basically like polar coordinates, but with an extra z, so nothing too bad. Let me just rewrite what I did in the Cartesian coordinates. Z stays exactly the same. And so z stays exactly the same. We have x here. X is equal to r cos theta times, so dv in cylindrical coordinates is r dz dr d theta, and 0 to x. So this is 0 to r cos theta. And look at the xy plane once again to figure out r and theta. R goes from 0 to 2, and theta goes from theta goes from negative pi over 2 to pi over 2. This is our answer for cylindrical coordinates. Now let's do spherical coordinates. I didn't write down the formula for cylindrical coordinates because it's quite easy to remember, but I'm going to write it down for spherical coordinates because it's hard to remember it all in your head. So spherical coordinates, what you need to remember these 5 things in spherical coordinates. X is equal to rho sine phi cos theta. Y is equal to rho sine phi sine theta. Z is equal to rho cos phi. X squared plus y squared plus z squared is equal to rho squared. And dv is equal to rho squared sine phi d rho d phi d theta. Okay, so let's get started. X dv. So we need to figure out what this is in spherical coordinates, basically. Let's look at the cylinder first. So x squared plus y squared is equal to 4. In spherical coordinates, this translates to rho squared sine squared phi is equal to 4. So rho sine phi is equal to 2. So rho is equal to 2 cosecant phi. So in spherical coordinates, this goes from 0 to 2 cosecant phi, since rho is the distance from the origin. So, and then x is equal to rho sine phi cos theta. Okay, now let's look at phi. Z equals x. So z equals x. I already know in for phi that the maximum angle is pi over 2 because of the plane z equals 0. Because phi goes from the positive z-axis all the way to z equals 0. That's like a 90-degree turn. So yes, pi over 2. Now the lower bound, let's look at what z equals x is. So z equals x in spherical coordinates, this translates to rho sine phi cos theta is equal to rho cos phi. So divide both sides by rho sine phi. Assuming rho is not 0, we get cotangent phi is equal to cos theta. And theta is equal to cotangent inverse of cos theta. This is our lower bound, the plane z equals x. So cotangent inverse, I'm running out of space, so I'm going to say cos theta. Okay, and lastly, we have the bound theta. Theta works exactly like in cylindrical coordinates. It's from negative pi over 2 to pi over 2. And that is our final answer.